Hello, welcome to AQA demola, and today's lesson we are covering intermolecular forces and electronegativity. It's a bit of a new topic when it comes to A-level, but I'll do my best to explain it. We're going to cover Pauling scale, different trends in electronegativity as well. Hope it helps. Let's get straight into it. Okay, so we're going to introduce a new term called electronegativity. And literally, definition right here, ability of an atom to attract the shared pair of electrons in a covalent bond. All you need to know, yeah? Every single element on your periodic table has electronegativity, right? And the charges within the bond aren't evenly distributed. So due to this phenomenon of electronegativity, it means that your charge within a bond is not equal. As you can see, a covalent bond here between X and Y, right? I've said that Y is more electronegative than X. Cool. So you can see that shared pair of electrons in red, the bigger circles in red, I can highlight them a bit more. You can see that they are closer to Y than they are to X, yeah? What does that mean? Well, it means the charges around the electron also are going to shift towards Y. Hence, you can see with the blue, there's a higher concentration of charge near Y, making it this delta minus, the negatively polarized. I'll just highlight the delta symbol, yeah? Whereas, if there's less charge near to X, it's going to be delta positive or positively polarized. And what you can get is the electronegativity values from this Pauling scale. So this is the Pauling scale of electronegativity. You can see here that the most electronegative element is fluorine. Yep. And that's basically it to do with the Pauling scale. If they ask you an exam, they will give it to you to interpret. Cool. Now we just need to talk about trends in electronegativity. So a longer period, we increase our electronegativity. You can see here that there's a lot more. If we say that the red is going to be a neutron, there's a lot more protons. Apologies. There's a lot more protons on the right element than on the left. Right, and if we have more protons with the same number of electron shells, what you'll get is there's this phenomenon called shielding. I've said that word a lot, but shielding, yeah, it's basically about having more electron shells, which means that it's going to be more difficult to remove an electron from that element, yeah, from the atom of that element. So we have more protons, same number of shield. The difference in shielding is negligible, very important. Hence, our atomic radius is going to decrease. Why? Because there's more protons, there's going to be a stronger attraction on the nucleus, from the nucleus, stronger attraction from the nucleus and those outermost electrons because we have more protons, yeah? And that will reduce your atomic radius, which makes us more electronegative. We want to pull in those electrons more because there's more protons in the nucleus, yeah? If we go down a group, what you'll see is that we have increased shielding, we have an increased atomic radius because there's just more electron shells. Hence, it means that that nucleus is going to struggle. It's going to struggle to get those electrons in. Hence, your electronegativity is going to go down. So, for example, you can see a lot of these in group 1, especially when you go down the periods, you can see with these elements here that the electronegativity values are really low. Yeah. And if you go across a group, a period, for example, you can see that they are increasing. So if we do in green, see across this period that we're starting to get an increase majority of the time in your electronegativity value. Cool. Okay, I appreciate this is another dense slide, but now we talk about intermolecular forces. And I wouldn't worry about defining it. I've never seen it asked before. But it's just the attraction between different molecules that are holding a substance together. So between those molecules holding a compound or substance together, yeah, we've got permanent dipole forces or interactions, yeah. These occur when you have a significant difference in electronegativity. So for example, if we went back to maybe like hydrogen and chlorine or something, you can see there's a significant difference if you look at that Pauling scale in the electronegativity. Here I said X and Y. So X is attracting that shared pair of electrons more tightly, more strongly onto it. So there's a high concentration of electrons or charge nearer to X. So this becomes your negatively polarized one. If you want to see my full writing, but negatively polarized X. Yeah, and Y is going to be positively polarized. What we're saying is that there can be an electrostatic attraction between these different molecules. If we accept that this is one molecule, and this is another molecule, right? We can have an electrostatic attraction between them, shown in the blue line, yeah? Between the delta plus and the delta minus. And that would be a permanent dipole-dipole interaction. And for example, you see that in hydrogen chloride and hydrogen bromide. Cool. Induced dipole-dipole, London forces, van der Waals forces, it goes by a lot of names, yeah? Just stick to one of them. But what we say is this whole process. So electrons are going to move around, yeah? So if we start setting a diagram, you're happy that electrons are going to be in this outer shell, just kind of moving. And what I'm saying is at one point, there's going to be an uneven concentration of electrons. So you can see here on the Y, especially, that those electrons are all concentrated towards that right-hand side. What we're saying is that at that point, you get what is called an instantaneous dipole. An instantaneous dipole. And when you have an instantaneous dipole, suddenly we have delta minus, delta plus, because the concentration of electrons is greater on one side than the other. It's not evenly distributed. Cool. What then happens is this charge, like, it's hard to describe, but it kind of like signals to this. So remember, like charges repel. So if there's repulsion, then that means electrons are going to be like, shoot, I don't want to be here. I'm going to start moving towards this side as well. Yeah, so you can see the electron starts to move towards the right again. Yeah, and then that's going to make an induced dipole. It induces a dipole in the next molecule. So then now this is your delta plus, and that is your delta minus. And that's how we create induced dipole London forces, Van der Waals forces, whatever you want to call it. Yeah, I put examples: iodine, chlorine, hydrogen gas. All of those, same element, same electronegativity. Yeah, so you'll get these when there's similar electronegativities between your molecules. And what I just really want to bring home is that these form simple molecules. So a simple molecule, literally substances that has an intermolecular forces being it together. So all of these things I've mentioned exist as simple molecules. What you'll need to know about them is they have a very, very low melting and boiling point, just because these forces are really weak. Really weak, not much energy is needed to overcome them. Fine. They also cannot conduct any electricity because all of these electrons are locked in bonding. So they're either locked in bonding or they're just in the atom, but there are no free electrons. All of them are localized. No free electrons means we can't carry any charge. Okay, and when it comes to intermolecular forces, hydrogen bonds are that guy, that him, the main character. Yeah? A hydrogen bond is an electrostatic attraction between a hydrogen atom, covalently bonded to a highly electronegative species or element, and the lone pair of electrons of a highly electronegative atom. I'm going to describe in better detail. Don't worry about definition, they will not ask. But when we talk about these highly electronegative elements, your hydrogen bonds can only form between hydrogen if it's bonded to fluorine, oxygen, or nitrogen. So you'll have it in HF, for example, you'll have it in water, you'll have it in ammonia. These are the main instances where you are going to see hydrogen bonding. Also, something like an alcohol, for example, you can see that there's going to be a bond between oxygen and hydrogen now. It's going to be one of these bonds. Hence, that can have hydrogen bonding as well. Cool. Let's do an example. So, I think it's pivotal to be able to show hydrogen bonding. So I've drawn two molecules of ammonia. And literally what you're doing is, we have a lone pair of electrons on the nitrogen. You should know this from the Shapes of Molecules video. Yeah. What I can say is that there can be an attraction between that and the hydrogen that's attached to a highly electronegative species like nitrogen. Yeah? So you can see this bond here, we'd call a H or hydrogen bond. I hope that makes sense. And it's really important to be able to draw hydrogen bonds in exam. Cool. When we get to water, water is kind of a special case. So again, I'm going to show you the same thing. I look at this oxygen, a highly electronegative species. It has lone pairs. Yeah? And you can see the hydrogen, delta positive. It can go to the lone pair. We can even have this hydrogen go to the lone pair as well. And both of those are hydrogen bonds. Yeah? I just need to make it very, very clear to you all that you do draw it from the hydrogen to the lone pair or from the lone pair to the hydrogen. Don't make that mistake in exam. Yeah? And there's very useful properties that water has because of this. A lot of them relate more to biology, but in terms of chemistry, the ones that we want to cover are going to be having a high melting and boiling point because your hydrogen bonds are stronger than other intermolecular forces. So if we compare the strength of a hydrogen bond to permanent dipole or London force, the hydrogen bond wins every time. Yeah. Hence, because of that being stronger, water has a relatively high melting and boiling point. Water boils at 100 degrees. You wouldn't expect that from a simple molecule, especially one with 18 electrons. Yeah. And we could say ice is less dense than water. When you think about the arrangement, solids, they make this compact shape where the molecules are kind of spaced out. So you can have a lot of gaps between it because of these hydrogen bonds. So those gaps allow it to have a low density. Okay, and suddenly it's question time. So you got two to try down. Sulfur exists as S8 molecules and chlorine Cl2. What is the difference in their melting points? And similarly, you got another question about silicon dioxide and silicon chloride, and you want to explain some structure and bonding why silicon chloride has a lower melting point. Okay, answer time. So Cl2, S8, both simple molecules. Yeah, both simple molecules. However, S8 has more electrons. Because it has more electrons, it means that the chances of these induced dipoles or these instantaneous dipoles forming is going to be a lot more. And because there's even more electrons to go with that, it means that we're going to get stronger forces. Just remember, more electrons, stronger forces. Yeah? Similarly, next one, I think I look at this and I say a boiling point or melting point of 1,713, impossible for a simple molecule. So I'm thinking silicon dioxide must be a giant covalent lattice because I've got silicon, which is a non-metal. I've also got oxygen, which is a non-metal. And in silicon chloride as well, two non-metals, but this one, the melting point is minus 69, so I'm thinking that's really low, probably a simple molecule. And then I just have to describe. So silicon chloride, simple molecule, as we said here. Then we can say that your London forces, Van der Waals, whatever you want to call it, are weak. Because they are weak, very easy to overcome. Yeah? And then if I was talking about silicon dioxide, I would say a giant covalent lattice. So giant covalent lattice. And then the covalent bonds are strong. These are the ones that are breaking now. So they're strong and they need a lot of energy to break. That is how I would go about answering those two questions. Hoping I haven't waffled on too much, but here are your A-star tips. Literally, I think a lot of this is just going to be knowledge. So know what bonding is present in the molecule you have. I think similar to the example that I did with silicon dioxide and silicon chloride, I just need you to know, is it metal or non-metal? That will tell you what type of bonding it is, or what bonding it can be, melting and boiling point. If I see a melting point of minus 69, I'm immediately thinking, this must be a simple molecular lattice. Yeah. No way a giant covalent structure or a giant ionic or giant metallic structure is going to have a melting point of minus 69. Yeah, it's way too low. Conductivity as well. If I was told that it can conduct, maybe that changes my answer. Not for the last question, but if I'm told it can conduct, I'm thinking it can't be a covalent lattice. Yeah, it can't be a simple molecule if it conducts. Cool. And then also diagrams really important. So like I showed with the ammonia and the water, just make sure that you're happy to do diagrams, especially to show hydrogen bonding or to show induced dipole or permanent dipole. I mean, it's just very useful to be able to do an exam. What do we not do? Don't confuse simple molecules with a giant covalent lattice. I've seen it done before. Please do not be that person. The Pauling's values of electronegativity, if shown, literally don't use your own knowledge. If it shows the Pauling scale values, use the Pauling scale values. Yeah, don't rock the boat. Just do what it's showing you. Yeah, and then hydrogen bonding for chlorine. Yeah, I think this is just another misconception. I think a couple of people think chlorine forms hydrogen bonding as well. If it does, if it doesn't, debate it with yourself. Yeah, your specification tells you that the ones that do hydrogen bonding is nitrogen, fluorine, and oxygen. So just stick to that. I hope that has been a useful lesson for you. I think it's kind of a topic that gets a bit overlooked in terms of people kind of understand it, but maybe they don't know how to explain it. So I hope this video was really useful. We've got the TikTok and the Instagram both at A*demola. Drop a follow if you can, please. Also, on this video, any questions that you have about anything I said or any suggestions for future videos, just let me know in the comments below. I do my best to answer all of them. Please like the video, subscribe to the channel. Really, really goes a long way. And I will see you in the next one. Bye for now.